Hello, my name is Andres Salazar, and this is my presentation for the conduction and radiation class. I'm going to talk about the numerical study and simulation of the transient heat transfer in a paraffin-filled aluminum heatsink. So essentially on this project, I try to use ANSYS Workbench to work on some transient thermal analysis and simulation for obtaining a couple of performance behaviors and metrics of different cases that I evaluate with this specific type of material under certain conditions. So first of all, the outline here, I'm gonna start with the introduction and motivation, then continue with the problem statement, geometry and cases that I work with, the material properties of the paraffin wax as well as the aluminum cases, modeling assumptions that we did for the project simulation methodology, results and comparison, engineering interpretation, and lastly, the conclusions of the project. So as an introduction and motivation for the transfer heat in PCM aluminum systems, um, paraffin PCMs can store a lot of energy, but they have extremely low thermal conductivity. This means that when you suddenly heat one side, the surface warms quickly while the interior heats very slowly. A typical engineering fix is to place a PCM inside an aluminum structures like fins to particularly spread heat deeper into the material. But fins also add aluminum mass, which creates thermal inertia. So the real question here is under transient heating, do fins actually help or do they slow down the PCM's response? The goal here is to isolate the effect of fin height, essentially a geometry property with no convection, no latent heat, so we can clearly see how the geometry alone shapes the transient conduction behavior. As a problem statement, I model a sealed aluminum enclosure filled entirely with paraffin wax, starting at 25 degrees Celsius. At time zero, one external wall is stepped to 80 degrees Celsius and held there. Everything else is isolated, so heat only enters from one side. The physics is intentionally simplified to conduction only, no convection and no phase change model. That way, the influence of geometry isn't masked by extra phenomena. And there are three main cases that are compared. The first one is the aluminum box with no fins. The other one is the short fins of about 10 millimeters fins, and the long one with 30 millimeters fins. Every other parameter is identical, so any difference comes purely from the fin height. As model assumptions to keep the model control, both aluminum and paraffin have constant isentropic properties. I include only transient conductions, no natural convection, no latent heat, and perfect thermal contact at all metal PCM interfaces. So the enclosure starts uniformly at 25 degrees Celsius and only one wall is heated to 80 degrees Celsius. Even though the model is 3D, results are evaluated using a central 2D slice since the geometry is uniform in depth. These assumptions strip the problem down to its conductive core so we can isolate the effect of fin height with no other competing physics. Now looking at the geometry, it was done on SolidWorks, so the enclosure is the same in all cases, 80 by 60 by 20 millimeters. Thickness, we have about 2 millimeters of the aluminum walls, and interior is fully filled with paraffin. The only changing feature is the fin height. The no fin case has a clean cavity. At the center, the short fin case adds two 10 millimeters aluminum fins, and the long fin case extends them to 30 millimeters. Fin thickness, spacing, and depth are identical in all cases, which means that any changes in heat transfer behavior can be attributed directly to the fin height. Now, looking more to the material properties, these are a couple of thermal physical properties that we have where I included density, thermal conductivity, specific heat, latent heat diffusion, and melting temperature range. So particularly here, paraffin conducts heat extremely poorly, so around 0.21 to 0.24 watts over meters per Kelvin, which means heat travels very slow inside them. But it has a high heat capacity and a large latent heat window. In the other way, aluminum behaves more likely the opposite way. It conducts heat extremely fast, but it also adds thermal mass to it. So fins can spread heat, but they also require energy to warm up. This contrast is exactly um, the design trade-off we are trying to understand under the transient heating. So once we complete selecting all of those property setups, here next step was actually working in our mathematical model. So the system is governed by the transient heat conduction equation in both materials with no internal heat generation. So that's the generic energy equation that we have right here. There also exists no internal heat generation, and particularly now talking about the phase change framework, we also modeled a couple of enthalpy formulations, liquid fraction defined over 52 to 58 degrees Celsius, but it was not implemented on this particular study. Model captures sensible heating only, no explicit latent heat, even though I would like to go into this depth of problems using ANSYS was extremely difficult for just this really basic project, but a couple of um, future recommendations can be done so that the project can be uh, obtained into a much more complicated and desired way for obtaining an actual like latent heat simulations and actual phase change simulations as we expected. The main problem here was like using CFD, so computer fluid mechanics was more complicated than expected, so I needed to complete it just using a thermal transient analysis. Um, a couple of other things that we can look over here is that the boundary conditions enforce the heated wall, the isolated outer surfaces, and continuity of temperature of heat flux across aluminum PCM interfaces. So the enclosure begins at 25 degrees Celsius everywhere at time zero. The heated wall jumps to 80 degrees and stays fixed on that point, and all other surfaces are adiabatic. Energy transfer happens only through conduction across the aluminum PCM interfaces. So from the simulation, we extract the transient temperature field, the average PCM temperature, the minimum temperature dip in the core, and the heat flux at the heated wall, and the response time for the PCM center to reach 52 degrees Celsius, which is the solidus temperature, and ideally will show the range or the specific point where the paraffin wax will start changing its phase to a more like liquid. So now talking a little bit about the numerical modeling and simulation procedure, you can see here on figure 7.1 the ANSYS workbench setup for transient thermal simulation for the aluminum enclosure under the configurations that we talked about. So the first thing that I needed to do here is create one transient thermal for each case. Then on engineering data, I added and created some of the characteristical material properties that we have because ANSYS doesn't have paraffin wax under its design library. So I needed to create my own material, make a research about it, and then do all the tables set up for being able to use this specific material. Then once we complete that on geometry, we needed to export the SolidWorks geometries that I did as a STP file to obtain the geometry. And once that's completed, just check that it was working correctly, it was correctly exported or imported. And then on the setup was just ideally creating all the settings that we're going to see right now. So three different transient thermal um, procedures were done, and you can see them on the screen right now. Now, talking a little bit more about the geometry import and domain definition. First thing again was the step files imported from SolidWorks into ANSYS Workbench. Two separate solid bodies are defined. The first one is just the aluminum walls, then the aluminum walls with the fins, and then the aluminum walls with the fins and with the larger fins. So we also have another body that was the PCM region. So in SolidWorks, this is defined as two different solid bodies, the encapsulated enclosure and what goes inside the cavity. So another thing, important thing that was modeled here in SolidWorks is that identical array geometry across all of the cases. So only fin height varies. And then on material definition is also imported on the design libraries side. Talked you all about. Now, next thing that we can see here is the meshing that was done for this specific simulation. So we use a 3D unstructured tetrahedral mesh. The thing that I did here is following a couple of the steps and videos that I learned from ANSYS was essentially creating a local refinement near the fins and as well as the corners of the shape. So it has a better convergence on the solution whenever we are dealing with the simulation and mathematical models that are imported into our solution for ANSYS. So also created a mesh on the aluminum to PCM interfaces, fin bases, and heated wall. So we check for the mesh sensitivity that it performs in the best way possible. On the solver settings, was using transient thermal physics. Total simulated time was 2000 seconds, and time step was 2 to 5 seconds. So using just ANSYS automatic stepping, and it was done using the solution for default ANSYS thermal conversions and tolerances. Now, the boundary and initial conditions that we talked first, you can see here that the boundary is that a specific wall heated up to 80 degrees Celsius, and the other surfaces are specified as adiabatic outer surfaces. Now, thinking a little bit more about the post-processing metrics, again, we extracted values from the different spatial evolution setups, so 100 seconds, 500 seconds, 1000, 1500, and 2000 seconds. So that shows heat penetration depth in fins induced, essentially spreading into the fins on this temperature behavior. So to compare designs, essentially we exported these temperature fields at several times, computed the volume average PCM temperature, tracked the coldest region, evaluated transient heat flux at the heated wall, and measured the time when the center hits the solidus temperature. These metrics give both the global heating behavior and the local heat spreading behavior, providing a clean comparison of how fin height affects conduction. So now looking at a couple of the simulation results comparison of the three cases for the temperature behavior. The first one is the no fins cases. Second one Well, that one is the long fins cases, and then the third one is going to be the short fin cases. So you can see that each one is evaluated under the same metrics and parameters, and the result data was then exported into Excel table and evaluated on the results table. This right here is the simulation results comparison for the three cases, comparing essentially the heat flux and how it is affected for the different fin configuration to check if that actually creates any kind of decrease or improvement on the performance of heat being transferred, and particularly move into the paraffin wax. So now looking at the temperature field evolution PCM heating behavior data results that we obtained, particularly on the temperature field results, the center reaches 52 degrees the fastest with the no fins configuration with about 189 seconds. The short fin reaches it slightly later with about 205 seconds, and the long fins reach it much later at around 235 seconds. So what this tells us essentially is that the added aluminum mass from the fins slows the early stage heating, even though the fins improve lateral spreading. By mid-time, the fields look really similar, and by the 2000 seconds, all cases converge to about 78 degrees Celsius average. So fin height changes early behavior, but has almost no effect on long-term conduction dominated temperatures. So here are a couple of the benefits as well as like the actual significant values that we obtained from this experiment. Now looking at this specific plot, here's where we did the actual comparison of the three different configurations. We're looking at the volume average PCM temperature over the full 2000 seconds transient configuration. So all of these three cases follow almost all the same trend, a rapid initial increase as lower mid-stage rise, and then a convergence near the 78 degrees Celsius. These main takeaways that the fin height only affects the early part of the heating process again. The no fin case warms slightly faster because it has the least aluminum mass, while the fine cases lag a bit due to thermal inertia. But after around 1,200 seconds, we can notice that all three cases essentially, um, particularly here, converge on this area, um, showing that under pure conduction, fin height has a really limited impact on the long-term temperature for the PCM. Now here also we have a couple of examples related to the heat flux results. We can see the, not heat flux, but the temperature behavior results. This is a way that the procedure was done. It was set up to 1,000 seconds, evaluate the local minimum and maximum for the temperature behavior, and then those data and averages, minimum and maximum, were just put on the Excel sheet and extracted from the Axis workbench, and then proceed to download the performance calculation metrics. So you can see here the one for the no fins configuration, short fins configuration, and the long fin configuration. So the heat flux behavior at early times, what we have from this specific analysis is that the fine configurations draw more heat up to about 13 kilowatts per meter cube, sorry, square. So for long fins, uh, essentially what we understand here is that fins reduce thermal resistance near the heated wall. So they allow the wall to release more energy initially, but as the PCM warms, the gradient collapses and all cases converge to more similar heat flux levels. So fins affect the rate of energy entry, but this doesn't translate to a proportionally faster PCM heating due to their added thermal mass. So here we start like seeing a couple of stuff related to the project. Even though the results that were pursued were obtained, it wasn't showing actually like too much of a significant change in what it has to be on the heat flux behavior, rather than on the temperature behavior. We can see a couple of more specific and more significant results. Particularly here on the heat flux of the heated walls, we can see that on the figure shows how much heat each configuration pulls from the heated wall over time. So early on, the fine geometries um, draw more heat, especially the long fins, but because they reduce thermal resistance and spread conduction more effectively in the aluminum region, as the PCM warms and the temperature gradient decreases, the heat flux for all cases drops sharply and eventually reaches similar values right here. So the key message here is that the fins increase the initial heat transfer into the system, but that doesn't translate into a much faster PCM heating rate because the additional aluminum mass introduces extra thermal inertia for the assumptions that we did for this specific project. Now looking to the actual heating rate comparison and interpretation, when we compute the simple heating rate from 200 to 1,000 seconds, the no fin case is the fastest, followed by the long fins and then to the short fins. So the difference are really small, but the trend is consistent with the response time behavior that we expected. Under pure conduction, the thermal inertia of the aluminum has more impact than the conduction benefits of the fins. Um, We can also see here, like essentially, again, highlighting that the no-fin case hits PCM core faster despite having no internal conduction pathways. And then scope and constraints of the conduction only model. Here's a couple of the model limitations that I had for this specific project. Again, I was trying to and expecting to develop this as a phase change on the PCM to actually obtain more like a latent heat result solution formula, but it was just too complicated to do. Nevertheless, this space set up a really good um, topic and baseline to start working on this project and then follow it up with a more complex calculations, as well as actually being able to use this computational fluid mechanics in the future and evaluate performance in a better way. A couple of things here is that the results reflect conduction only. They do not include convection inside the melted PCM, latent heat absorption, and temperature-dependent material properties or realistic heat loss conductions, which are a couple of limitations that the project has. But the fin height is the only variable, so the study doesn't explore full fin topology, as it could be better. The model is intentionally simplified to create a baseline before adding a more complex melting physics, essentially. Uh, Now, a couple of the transient conduction insights for the PCM aluminum systems. This is mainly the conclusion for the project. What I can say about it is that in the early stage, no fin warms the PCM core the fastest because the system has the least thermal mass. Fins improve lateral heat spreading, but delay the core response in the mid and late stages. All cases converge to nearly identical temperatures, so for short transient heating events, fins may not be beneficial. For long duration heating, fins height becomes less important. So these findings establish a clean conduction only baseline that prepare particularly this project for future models, including convection and latent heat, which could be evaluated on CFD analysis. Thank you.